A single thread catches the light, no thicker than a strand of hair, yet strong enough to have clothed emperors and financed empires. It did not begin in a factory. It began inside the body of a caterpillar, secreted as liquid protein, hardened the instant it met air. For thousands of years, that thread moved silently between continents, carried by traders who understood its value, but not its origin. Elsewhere, a single drop of amber liquid falls from a broken honeycomb, catching sunlight the way molten glass might. Inside a hive the size of a shoebox, tens of thousands of workers coordinate without a single command center, without a leader issuing instructions, without a blueprint. And beneath a savanna sky, a mound of packed earth rises 8 meters into the air, built grain by insects with no eyes and no architect among them, yet regulating its internal temperature more precisely than most human-built structures manage today. 3 materials, 3 civilizations transformed, none of them invented by human hands. Silk built the Han Dynasty's wealth and stitched together the trade network later named for it, the Silk Road. 4,000 miles of desert and mountain crossed for a fiber spun by an insect smaller than a fingertip. Honey sweetened, preserved, and fermented the diets of ancient Egypt, Mesopotamia, and Rome, its production so vital that Egyptian pharaohs were entitled Bee King as a mark of dominion. And beneath the earth of Africa and Australia, termite colonies engineered climate control systems so effective that 21st century architects would eventually copy their design to cool an entire office building without air conditioning. None of these insects planned any of it. None possessed anything resembling a brain capable of foresight. A silkworm's entire nervous system contains roughly 10,000 neurons, a fraction of what exists in a single human eye. A honeybee's brain weighs less than a milligram. And yet the structures, materials, and systems these creatures produced became foundational to entire economies, dictating what nations traded, fought over, and built their identities around. The uncomfortable question emerging from the wreckage of that assumption is this: if these insects never intended to shape civilization, what does it mean that civilization organized itself around their biology anyway? Somewhere between instinct and infrastructure, between a creature that cannot think and a species that believes itself uniquely capable of building, something does not add up. And of the 3, one still holds a secret no engineer has fully cracked. Its ventilation system, built without blueprints, without tools, and without a single directing mind, performs a feat of airflow regulation that modern fluid dynamics has yet to completely explain. That structure is still standing, still breathing, still working, right now, silently, underground. The story most often told about silk begins with an empress. Around 2700 BCE, according to Chinese legend, Empress Lezu sat beneath a mulberry tree when a cocoon fell into her cup of tea. As it unraveled in the hot liquid, she noticed a single continuous filament, and silk was born as a courtly discovery. A gift from nature to nobility. It is a clean story. It is also almost certainly myth. Archaeological evidence tells a rougher truth. Cocoon fragments recovered from Yangshao culture sites in Henan province date silk production back to at least 3600 BCE, over 1,000 years before Lezu's supposed lifetime, in communities that were agricultural, not imperial. Silk was not a gift discovered at court. It was engineered slowly, generation after generation, through relentless selective breeding of a wild moth species until the domesticated version, Bombyx mori, could no longer survive without human intervention. Here is the complication historians rarely emphasize. Modern silkworms cannot fly. Their wings, though present, are vestigial, incapable of lift. They cannot forage, cannot escape predators, cannot reproduce without direct human handling of their eggs. Across roughly 5,000 years, an entire species was reshaped so completely that it became biologically dependent on the very civilization that depended on it. Silk was never truly domesticated in the way wheat or cattle were domesticated. Something closer to mutual captivity took hold. An insect stripped of survival instincts in exchange for centuries of protected breeding. A parallel misunderstanding surrounds the honeybee. Beekeeping is widely assumed to resemble simple livestock management. Build a box, collect the harvest, repeat. But colonies operate on a form of distributed decision-making that has puzzled biologists for over a century. When a hive outgrows its space, scout bees depart independently, evaluate multiple potential nest sites, sometimes locations kilometers apart, and return to perform variations of the waggle dance, essentially casting votes through movement. The colony does not follow a queen's decision. It follows a quorum, reached through thousands of individual insects, weighing conflicting information against each other until consensus emerges. No central authority directs this. No single bee holds executive power. And yet the outcome consistently favors survival. A decentralized democracy operating entirely on instinct, older than any human system built to achieve the same result. By the time European guilds and Chinese dynasties had constructed entire economies atop silk production and honey trade, they had built civilization-scale infrastructure around organisms whose internal logic remained, and in many ways still remains, only partially understood. The myth of simple domestication concealed a stranger reality. Humanity had entangled itself with biological systems it could exploit long before it could explain. Inside a silkworm's body sits a pair of glands that function unlike anything humans have manufactured. Silk protein, called fibroin, is stored inside the worm as a thick liquid, a state scientists classify as a liquid crystal, meaning its molecules are partially aligned even in fluid form. As the worm forces this liquid through a narrow opening called a spinneret, shear forces and pH changes trigger near-instant molecular realignment. The liquid crystallizes into solid fiber in a fraction of a second at room temperature, using no heat, no toxic solvents, and no external machinery. Human polymer engineers, working with pressurized vats and industrial extrusion technology, still cannot replicate silk's strength-to-weight ratio using synthetic methods alone. That is the moment the myth collapses entirely. An organism smaller than a thumb had already solved, through unconscious biochemistry, a materials engineering problem still challenging laboratories equipped with electron microscopes and computational modeling software. A parallel discovery occurred an ocean away, on the cactus fields of Oaxaca, Mexico. There, a small parasitic insect called the cochineal, roughly the size of a ladybug, feeds on prickly pear cacti and produces carminic acid, a compound so intensely pigmented that when dried and crushed, it yields one of the most vivid reds ever recorded in nature. The Aztec and later Spanish colonial economies built entire export industries around this insect's chemical defense mechanism. It took approximately 70,000 dried cochineal insects to produce a single kilogram of dye. By the 16th century, cochineal red had become Spain's second most valuable export from the Americas, trailing only silver and European royalty, cardinals, and the British red coat military uniform, all depended on a defense chemical secreted by an insect to avoid being eaten by ants. For nearly 3 centuries, European chemists attempted and failed to synthesize a comparable red pigment. Spain, recognizing the insect's singular economic value, treated its biological source as a closely guarded state secret, restricting seed cactus and live insect exports under threat of severe punishment. The secondary complication is almost poetic. The compound that made cochineal insects commercially priceless existed purely as a predator deterrent. A chemical warning system evolved over millions of years to protect the insect from being consumed. Humans repurposed a defense mechanism into a luxury commodity, entirely blind to its original biological function. Multiply this pattern across silk-producing regions of China, honey economies of the Mediterranean, and cochineal fields of Mesoamerica, and a picture emerges of global trade routes, colonial expansion policies, and entire national treasuries constructed atop biochemical processes evolved for survival, not commerce. Engineering achievements no human laboratory initiated, only later discovered. Now scale the pattern upward to its most extreme expression. In the termite mounds of sub-Saharan Africa and northern Australia, colonies of macroterm species construct structures that tower up to 8 meters, the equivalent, proportionally, of a human civilization erecting a mile-high skyscraper using nothing but mouth-carried soil pellets. Inside these mounds, internal temperature holds remarkably steady, often varying by less than 1 degree Celsius across a full day-night cycle, even as external temperatures swing more than 20 degrees between scorching daytime heat and cold desert night. No termite designs this system consciously. There is no blueprint, no engineer termite issuing instructions. The mound's intricate network of chimneys, tunnels, and porous walls emerges through a process biologists call stigmergy. Thousands of individual insects responding only to local cues, each one modifying the structure slightly based on airflow and moisture it senses in its immediate surroundings. From millions of these microscopic, uncoordinated decisions, a coherent, functioning climate control system emerges at a macro scale no single insect perceives. Architect Mick Pierce studied this exact mechanism when designing the Eastgate Center in Harare, Zimbabwe, completed in 1996. An office and shopping complex that uses termite-inspired passive ventilation to maintain stable internal temperatures without conventional air conditioning, reportedly cutting energy consumption by roughly 90% compared to similarly sized buildings. Even with modern sensors, computational fluid dynamics software, and decades of biomimetic study, engineers have replicated only an approximation of the mound's efficiency, never the full mechanism. Now consider the stakes on the opposite end of the insect spectrum. Roughly 1 out of every 3 bites of food consumed globally depends, directly or indirectly, on pollination performed by insects, honeybees chief among them. When colony collapse disorder swept through commercial beekeeping operations beginning in 2006, entire hives were found abandoned within weeks. Worker bees vanished without explanation, leaving queens and larvae to starve. Almond orchards in California, dependent on migratory beehives trucked in from across the country each spring, face pollination shortfalls severe enough to threaten a crop worth billions of dollars annually. Remove the insect, and the infrastructure built upon it does not simply weaken, it collapses. Remove the silkworm, and centuries of textile economies vanish. Remove the cochineal insect, and colonial trade routes reroute entirely. Remove the termite, and savanna ecosystems lose their primary soil engineers, along with a design principle now embedded in sustainable architecture worldwide. Civilization, it turns out, built emergency-free contingency on organisms it never fully controlled, understood, or could easily replace. Strip away the myths, the legends of empresses and courtly discovery, and what remains is a single uncomfortable thread connecting silk, honey, cochineal red, and the termite mound. Civilization did not invent these systems. It found them already engineered, already functioning, refined over millions of years by evolutionary pressure rather than deliberate design, and simply built empires on top of what was already there. The Silk Road did not exist because humans invented fiber production. It existed because a caterpillar's liquid crystal biochemistry produced a material strong and beautiful enough to be worth crossing deserts for. Spain's colonial economy in the Americas did not rise purely from military conquest. Part of its wealth rested on a defense chemical, secreted by an insect to avoid being eaten by ants. And when modern architecture searched for a genuinely sustainable model of passive climate control, it did not turn to a laboratory. It turned to a mound of dirt, built by a creature without eyes, without a brain in any conventional sense, operating on nothing but localized instinct passed down since the Cretaceous period. What remains unresolved, what still resists complete explanation, is the termite mound's precise mechanism of self-regulating airflow. Researchers have proposed multiple competing models: wind-driven induced flow, thermal convection stacks, metabolic heat exchange through porous walls. Each model explains part of the phenomenon. None fully accounts for the mound's consistency across wildly different environmental conditions, across different termite species, across mounds built in isolation from one another with no shared blueprint. A structure with no architect continues to outperform structures designed by architects holding advanced degrees. Consider what this means. Quietly, beneath the historical pageantry of silk-clad emperors and gold-lined cathedrals dyed in cochineal red, the materials and systems that financed dynasties, dressed royalty, sweetened diets, and now inspire sustainable design were never human inventions at all. They were discoveries, biological processes that existed long before any city rose to claim them. Refined by insects operating purely on survival instinct, indifferent to the empires that would one day depend on them entirely. Somewhere beneath a termite mound standing silently on a savanna right now, air is moving through channels no engineer designed, regulated by a system no scientist has fully mapped, built by creatures who will never know their construction, outlasted the civilizations that studied it. And somewhere in a museum case, a length of silk thread, spun in seconds by an insect blind to its own genius, still holds its shape after centuries. A quiet reminder that the line between instinct and intelligence may never have been as clear as the species who named itself for building things once assumed.